the Moivries theorem and trigonometric functions.
All right, today so we want to look at algebra, the Moivries theorem. So take note that the Moivries theorem was derived from the polar representation of the what do you call of the complex numbers. So the Moivry is a scientist. So his theorem was actually derived from his theorem was derived from the polar form of a complex number. The polar form of a complex number. So take note. Now, the Moivries says that since um, if E of I theta, E of I theta, exponent I theta, all exponent n will be equal to E of I theta n, then we can say that cos theta, because then we can see that if also then if you see since this is equal to this, then if I theta is equal to cos theta plus I sine theta, then we will have U of I theta all exponent n to be equal to cos of cos theta plus I sine n theta all exponent what n, all exponent n. So now that is why he's saying that if you have something like this, then it's the same as this, and this cos theta plus I sine theta all exponent n can therefore be equal to this, and this also to establish that will be equal to cos n theta plus I sine n theta, and this is the Moivries theorem. This is what we refer to as what? The Moivries theorem. This is the Moivries theorem. All right. Now, with the Moivries theorem, there are three basic applications you have to know. Three basic applications. So out of those applications, that is where you can tackle a question on a complex number in a polar form. And these three basic applications. So three basic applications and that the Moivries theorem. One, we'll be using the Moivries theorem in trigonometric identities. In trigonometric identities. Using the Moivries theorem in trigonometric identities. Two, we'll be using the Moivries theorem in finding the n truth. In finding the n truth of unity. In finding the n truths of unity. And three, we'll be using the Moivries theorem in solving polynomial equation. We'll be using the Moivries theorem in solving polynomial equation. So these are the three basic applications where we'll be using the Moivries theorem. Three basic: one, trigonometric identities; two, finding the n truth of unity; and three, solving polynomial equation. So for the sake of this video, we want to look at the trigonometric identities. Okay, so now we want to look at how we can use the Moivries theorem in what? In trig identities. So what happens is that before we can do this, we consider the expression of a multiple angle function in terms of a polynomial in a single angle function and its converse. So I want you to write this down. To do this, you have to one, you consider the expression of a multiple angle function to consider the expression of a multiple angle function in terms of polynomial. In terms of polynomial in the single angle functions and its converse in a single angle functions and its converse. So in the how to before we can use the De Moivre's theorem in finding trigonometric identities or in trigonometric identities, this is something you have to take note. That first of all, you will consider the expression of a multiple angle function in terms of a polynomial in the single angle functions and what its converse. Its converse. Sorry. So now example one. We want to look at how we can express sine 3 theta and cos 3 theta in terms of powers. So this is a typical question they can give you in terms of powers of cos theta and sine theta. Full stop. Using the Moivries theorem. So now, this is a typical question that you can be given, that express sine 3 theta and cos 3 theta in terms of powers of cos theta and sine theta when we want to use what? The De Moivre's theorem. And let me think here so that we can look at this question at this very point. Okay. So now, the question gave us sine 3 theta and cos 3 theta. I want to do this expression in terms of the Moivries theorem. Okay, so now what can happen is that with the Moivries theorem we came about, we said that if we have cos theta, if we have cos of what? N theta plus I sine n theta. This is the De Moivre's theorem. Then it is equal to the cos theta plus I sine theta, all exponents the n. All exponents and n. And this is the De Moivre's theorem. This is the De Moivre's theorem. So now what happens is that if you want to do this, then you can have cos 3 theta plus I sine 3 theta. We want to express this in terms of what? In the powers of cos theta and what? Sine theta. So that cos 3 theta plus I sine 3 theta can give us what? Cos theta plus I sine theta, all exponent what? 3. N. All exponent 3. So we are using the De Moivre to expand this in terms of cos theta and sine theta. So now you have cos theta on its own and sine theta on its own. Alright. So now when you have this, then we expand this. So now if we expand this cos theta, I sine theta. So when you expand it, this is how you get. Let me just take my time and go through for you. Multiplying cos theta plus I sine theta. Multiply another cos theta plus I sine theta. Alright, so when you do this, when you multiply it together, when you are done with the multiplication, this is what you'll be getting. You have, this will give you cos square theta. This will give you cos square theta plus I sine theta. I sine theta cos theta. So we come to this side too, we get what? I sine theta cos theta. Please, you should watch me very carefully. Now we come this here and here, and we have plus what? Now the I square, to give you I square, and I square is equal to negative 1. Take a look. So now, because it's negative 1, we get minus what? Sine square what? Theta. Okay, so we are done with this, and we multiply this with the last one, which is cos theta plus what? I sine what? Theta. Alright. So now we want to multiply this also with the last one. So now we get cos theta times cos square theta times cos theta. Now give what? Cos cube theta. Cos square theta times I sine theta. So we get plus I sine theta cos square theta. Alright. So now we get this and this too. So plus I sine theta cos square theta. Alright, and this one also multiply this one, which we get I square. So we get what? Minus what? Sine square theta cos what? Cos theta. Now we come to this side too, which will get the same thing. This one will multiply this, so we get what? Plus I sine theta cos square theta. I sine theta cos square theta. And we will come to the last one here. So when we come to the last one here, what will we be getting? This multiplying this one multiplying this, you get minus, because it's II, which will give us minus sine square theta cos theta. And now we come to the last one. So the last one here, when we expand it, we get what? Minus sine square theta cos theta. And last one here, we get minus I sine cube theta. All right. So now when we do this, we'll be done with the expansion. Now realize that there are some of them we still have the I over there, and there are some of them we don't have the I. So let me clean this side and see how we can do that. So those who have the I, when you summarize everything, you get what? Cos 3 theta, cos cube theta plus cos cube theta, which is here, minus 3 cos theta sine square theta. So now you have this one with no I. Okay, you have these two with no I. All right, you have these two with no I. You have these two with no I. All right, so now when you do that, you are getting, minus 3 cos theta sine what? Square theta. Plus, the rest of them has I. This has I, this has I. Okay, this also has no I. Okay, so now the rest of them are having I. So this has an I, this also has an I. So we get I into bracket. Okay, let me clean this side so now I'll extend it. So we get I into bracket 3 sine theta cos square theta minus sine cube theta. All right. So now we got those also what with the I. Yeah, we got those also with the I, and plus 3 sine theta cos square theta minus that. Okay. So now when you're done with everything, this becomes your total expansion. Do you get it? This becomes your total expansion, and this becomes your total expansion. Now tells us that if you want cos 3 theta, if you now want cos 3 theta, it is equal to what? Cos cube theta minus what? 3 cos theta sine square theta. So the cos 3 theta goes to what? Because cos theta always is the real part of what? Of the complex number in terms of what? The polar representation. And this one gives you what? If you want to expand this very well, we know that sine square theta is the same as 1 minus what? Cos square theta. So since you know this, in trigonometric identities, what you can do is that, therefore, our cos 3 theta now becomes what? When you put 1 minus cos square theta here, you now be getting 4 cos cube theta minus 3 what? Cos theta. And that becomes the expression for what? Cos theta. So now instead of express this one in terms of cos theta, so we are done with that one. So now I want to express sine 3 theta too. And sine 3 theta was the imaginary part, which you got as 3 sine theta cos square theta minus sine cube theta. Now, this one that we have here too, we can also decide to expand this one. And now when you expand this one, what you get is that cos square theta is the same as 1 minus what? Sine square theta. So therefore, when you put 1 minus sine square theta into this equation, you'll be getting 3 sine theta minus 4 sine cube theta. 4 sine cube theta. And that is the expression. Okay. So now, the same question we have, we said that when you bring it from what? The multiple angle. So the multiple angle here was what? The 3 theta, which is a multiple of the theta. And we brought it to a single function. A single angle function in the form of only theta, no other n value attached to the theta. Are you getting it? Okay. So now we brought it there. We can also find its converse. Find its converse. So let's do with the converse over here. How do we find the converse? So the converse is when we have the converse uses z is equal to what? E exponent what? I theta. Okay, so this is the final for the expression. Now let's look at the converse in the trig function. So now, the converse uses z, which is equal to what? E of what? I theta. Z, which is equal to what? E of what? The I theta. So now what happens is that with the converse, you can have, first of all, the expression is Zn plus 1 over Zn, which is equal to what? 2 cos n theta. And you can also have the expression like, there are two expressions, so one is this, and two. If you have any expression like Zn, a complex number minus the inverse of that complex number, then it is the same as what? 2i sine n theta. 2i. So this is the converse. Take note of this very well because you will be using it. So in the trigonometric identities, in using the Moivries, you can use it in the first aspect whereby you convert, we consider the multiple angles in terms of what? The polynomial for the single angles, angle functions, and after we find its converse. So this is how we deal with the converse. Now let's look at how we go about it. So if you have something of this nature, z is equal to this, and zn, that means our zn is always equal to u of I theta all multiplying what? N. And that brings an idea of what? The Moivries theorem, which is also equal to what? U of I theta n. Okay, so now you have this. If you have Zn plus 1 over Zn, then what we can say that one is equal to cos theta plus I sine theta all exponent what? n. So now the first Zn is equal to this. And the second Zn, which is 1 over n, 1 over the inverse of 1 over Zn becomes what? The cos theta plus I sine theta exponent negative n. I get it. So anytime you have 1 over Zn is the same as Z exponent negative n. So that's what we've done here. So 1 over Zn plus Z exponent what? Negative n. Alright. So if you understand this, then we can try and simplify this also. So upon simplification, we get what? Cos n. This one can now turn to be this one. So we get cos n theta plus I sine n theta plus this place also we got cos of negative n theta plus I sine negative n theta plus I sine negative n theta. So finally, you'll be getting cos of n theta plus I sine of n theta plus cos n theta minus I sine of n theta. Okay, so that's it, minus I sine of n theta. What it means is that anytime you have cos of a negative value, maybe cos of negative a, it is the same as what? Cos a. But anytime you have sine of negative a, it is equal to what? Negative sine a. Take note. This is something you should know from your calculus in your secondary school. So if you have cos of negative a, it is the same as cos a. Sine of negative is the same as negative sine a. So that's why in this place, negative n theta became plus cos n theta. Alright. So now, when you simplify this, what happens is that this will take this away. So cos n theta now becomes 2 cos what? N theta. So that's how we got this. So Zn plus 1 over Z exponent n is equal to what? 2 cos what? N theta. I want you to try this. I'm not solving this in this video. I want you to try this on your own. And when you try it, the final answer you're getting is what? 2i sine n theta. When you try that one, that will be the final answer. Or the final expression you'll be getting. The final expression you'll be getting after this would be what? Cos n theta plus I sine n theta minus cos n theta plus I sine n theta. So this is the final expression you'll be getting. So the cos n theta will take this one away, and you finally get the 2I sine n theta. But in all, these are the two things you have to put in your head. These are the two major things you have to put in your head, and that is called the converse. And that is called the converse. Now, let's look at when z is equal to 1. Sorry, when n is equal to 1. So the expression, if you have when n is equal to 1, that is you're getting z1 plus 1 over what? Z1. So you can just put it this way. And if that's the case, then you simply get 2 cos what? 1 theta. There'll be no what? There'll be no n. 2 cos 1 theta. And the same, if you have z minus 1 over z, it's the same as 2I sine theta. There'll be no n. So that is when n is what? Is equal to 1. Let's take an example so that we can end this lesson. Let's take an example here. All right, so the question says find an expression. Find an expression for cos cube theta. Find an expression for cos cube theta in terms of cos 3 theta and cos theta. So now you realize that when we did cos 3 theta, we had 4. When we did the cos 3 theta, we had what? 4 cos of cube theta minus what? 3 cos theta. So now we are finding a way where we can also take the single cos function into the multiple angle function. I get it. That is the converse. Do you get it? So the converse is finding where we can take this cos theta and the 3 cos theta, the single functions, into the what? The multiple angle functions like this. I get like the cos 3 theta. I get it. And that's the converse. So now to do that, you have to apply the z plus 1 over z or the z minus 1 over z. All right. Okay. So now in terms of the sign, you apply the second one, the z minus 1 over z. But in terms of cos, you apply the first one, which is z plus 1 over z. And that is the trick to it. Okay, so this is the question. How do we tackle this question? How do we tackle this question? And it's very simple to also do it. So now, what happens is that if you have your cos of 3 theta, okay, solution. Your cos of 3 of the cube theta is equal to 1 over 2 cube. It's 1 over 2 cube into bracket z plus 1 over z cube. I get it. So this is your expression. Your cos of the 3 cube, the cube theta is 1 over 2 cube, or into bracket z plus 1 over z cube. This expression is very simple. It's in your what do you call, finding, I think, under angles. Yeah, under angles. Anytime you have cos 3 theta, cos cube theta, this is how you express it. This is how we express it. Are you getting it? So now after you are done expressing it, what do we do? We can now do with expanding this. So we have 1 over 8. This is 2 cube. So you have 1 over 8. Okay. Z plus 1 over z cube. So now let's do with our z plus 1 over z cube. Sorry. So our z plus 1 over z cube will also be very, very simple here. And when we expand this, we get z cube plus 3z plus 3 over z plus 1 over z cube. So when you expand z plus 1 over z cube, this is what you get after your expansion. You can try this. This is your simple mathematics. So now when you get this, what happens is that you can now have 1 over 8 into bracket z cube plus 3z plus 3 on z plus 1 on what? Z cube. Okay, so the moment you have this expression, you can easily group the expression into 2. So now you realize that we have the cube part of the expression and you have the single part of the expression. So now you can see that you have 1 over 8 into bracket, 1 over 8 multiplying this. So now you have, let's multiply through by 1 over 8. So you multiply through by the 1 over 8, you have z cube all divided by 8 plus 3 over 8z plus 3 over 8z. This one is 3z over 8, and this 3 over 8z, that is here, plus 1 over 8z cubed. All right. So now this is the expression you are getting. So now we can group the 8 part, the z cube part, which becomes z cube over 8 plus 1 over what? 8z cube. So now when we group this part, and we also group this part with plus here to 3z over 8 plus 3 over 8z. All right. So now, after we are done grouping this section, this part, what can we get? We can see we have 1 over 8. Factor 1 over 8 out here. We get 1 over 8 z cube plus 1 over what? Z cube. All plus, here we can factor 3 over 8 out. So factor 3 over 8 out, we are getting z plus 1 over what? 1 over z. And when you do that, z cube plus 1 over z cube, you have zn plus 1 over what? Zn was equal to what? 2 cos what? N theta. So therefore, this one simply becomes 2 cos of what? The cube, which is what? 3 theta. 2 cos of the 3 theta plus, take note, we are expressing in terms of cos 3 theta and not the cos theta. Are you getting it? So this one also becomes 3 over 8 to bracket 2 what? Cos what? Theta. Are you getting it? So just this one will give only 2 cos theta. So now when you solve this, your cos cube theta will now be equal to 1 over 4. So that will be 1 over 4 cos 3 theta plus 3 over 4 cos what? Cos theta. Okay, and this brings us to the end of what? Using the Moivries theorem, trigonometric identities. I want to get some questions and solve so that I can move on to finding the nth root of unity.